All right, we are going to start on section 9.3, changes in temperature and phase. Now, in order to discuss what happens during phase changes to substances, which is pretty interesting, we have to define some terms and look at some kind of formulas and equations. So the first thing we're going to talk about is specific heat capacity. And this is a constant variable. It's the quantity of heat required to raise a unit of mass of homogeneous material 1 Kelvin or 1 degrees Celsius in a specified way given constant volume and pressure. What that is the specific heat capacity is different depending on your object. So water always has a very well-known specific heat capacity. Gold has a well-known specific heat capacity. Aluminum, silver, copper. And so I've given you a table of those values, and depending on your material, it's going to have a specific or a set specific heat capacity. It's basically a measure of how easy a substance is to heat up, or how well a substance conducts heat, how well it transfers heat. So gold, which conducts heat very, very well, has a small heat capacity, specific heat capacity. Water, which does not transfer heat very well, has a very high specific heat capacity. So it kind of tells you how well something conducts. Metals will always have pretty low, non-metals, and water is going to have high ones. And this leads us to the idea they use these specific heat capacity of water. They use it to determine how heat is transferred from, or how much heat an object has. Sometimes they can use it to figure out how much the specific heat capacity is of another object. So here's an image of it. What they do is they have this chamber that is full of water. They can measure the increase of water in the chamber. It's very well insulated. And then what happens is they put a test substance in there. They may know the initial temperature of your test substance. It goes in there. They measure the change of the temperature in the water, and they can figure out the specific heat capacity of the object. Or sometimes if they need to know something else about it, say the initial temperature, how hot it actually was, etc., they can do that too. And this procedure is called calorimetry. And it's an experimental procedure used to measure energy transferred as heat from one object to another. So let's say we know the specific heat capacities of these objects. We can actually figure out energy as heat. Energy as heat isn't actually all that easy to measure. So we have to use other things that we can measure to figure this out. And it's using this equation here. Your heat, if we rearrange for heat, you have Q is equal to the specific heat capacity times the mass times delta T. You should have used this in chemistry. I know we do it in physical science too. And it's pretty simple equation. And we're going to look at the changes in our first example problem. So a 0.050 kilogram metal bolt is heated to an unknown temperature. It is then dropped into a calorimeter containing 0.15 kilograms of water with an initial temperature of 21 degrees Celsius. The bolt and the water reach a final temperature of 25 degrees Celsius if the metal has a specific heat capacity of 899 joules per kilograms times degrees Celsius. Find the initial temperature of the metal. Now, one thing, if you did do this in chemistry, your specific heat capacities were joules per grams times degrees Celsius. In physics, they really work hard to always use kilograms. But in chemistry, they tend to not care because they use grams so often anyway. because they're usually using small amounts. So what do we know? We know the mass of our bolt. We know the mass of our water. Looking at our table, I can find the specific heat capacity of water, and they told me the specific heat capacity of my bolt. So I know the change in my water went from 21 to 25. So 25.0 minus 21.0 is 4.0 degrees Celsius. And that my bolt was also at 25 degrees Celsius at the end of my problem. So I know that the heat that the heat transferred as energy into the water is equal but opposite. So the heat in the water increased, the heat in my bolt decreased, but it's an equal, the magnitude is equal. So my heat is equal to my specific heat of my water times the mass of the water times my change in temperature of my water, which is equal to the specific heat of my bolt, the mass of my bolt times my change in temperature of my bolt. Now I'm looking for my initial temperature, so I need to change this into TI, F minus TI. Bolt. Okay, and now I'm going to distribute and solve for this. Oh, okay. Actually, I'm going to divide by this. Okay. So I end up with TI is my I've dropped a negative. So remember, these are negative. So when you divide by this, you end up with negative here. So you can add it. You end up with specific heat of your water, mass of your water, change in temperature of your water. Divided by the specific heat of your bolt times the mass of your bolt. All right. So we just put our values in. 25.0 plus 4186 times 0.15 times 4.0 divided by 899 times 0.050. I end up with an initial temperature of my bolt of 81 degrees Celsius. Okay, in problem 2, you're looking for the final temperature of everything. So remember, when you have your gold bar and your water, they end at the same final temperature. So you'll have to kind of get the TF by itself algebraically. In number 3, you're just looking for the mass of your copper coin. Remember, you must change from grams to kilograms. So give those a try, and then we're going to talk about phase changes. Okay. So we know that a phase change is when we have a substance that is changing from either a solid to a liquid or a liquid to a solid. This is known as fusion. Or a liquid to a gas or a gas to a liquid. This is known as vaporization, phase change. What happens is as, say you have a block of ice and you bring it out of the freezer, it would increase in temperature until it started melting. Once it starts melting, it maintains a steady temperature of 0, even though there is heat being added to your substance. That heat is going into other things. And then once you all have water again, you have a steady increase of temperature until your water is changing from liquid to gas. During this phase change, it stays at a constant 100 degrees Celsius. Then once it's all steam, it can increase again. Now, we call this increase, what happens is during the steady increase segments, you can use mass, specific heat capacity of your ice, water, or steam, and the temperature increase to determine how much energy is added during these segments. So you can find Q during these segments based on the mass, the change in temperature, and your specific heat capacity. During phase changes, what happens is, because that energy added not during phase changes, during these steady increases, that's going into increasing its temperature. During phase changes, however, these spots here, the energy added increases the internal energy without increasing the temperature. So consider with, let's say you have a solid, or let's start with a solid. You have, when you're changing, you're changing the solid's potential, the internal potential energy during a phase change. Potential energy is present among a collection of particles in a solid or liquid in the form of attractive bonds between particles. So if you're going from a solid to a liquid, some of that energy is going into breaking those attractive bonds. And if you're going from a liquid to a gas, same thing. That energy is going to breaking those attractive bonds. The bonds result from the charges within the atoms and molecules. So remember from our last chapter that potential energy, or a couple before, is associated with the electric forces between these charges. So what happens is you have your latent energy. I'm sorry. So if you can see this, latent energy is the energy per unit mass that is transferred during a phase change of a substance. So what happens is that latent energy is being added, and that energy is going into changing the attraction between molecules. So phase changes result from a change in potential energy of a substance. When energy is added to a substance during a phase change, the particles rearrange themselves to make up for their change of energy. The rearrangement occurs with no change of kinetic energy of particles. So they're kind of just rearranging their form so that their kinetic energy is, if you're going from a lower energy to higher energy, increased. But the kinetic energy of their particles is staying the same. So potential energy is increasing, but kinetic energy is staying the same during phase changes. And we call this energy that's added latent heat, and we can find it by taking Q, our latent heat, is equal to the mass times this latent heat value L. So latent heat is L, and we can find the heat added, Q, by multiplying our mass times our latent heat of whatever process this is. So we're going to actually practice this. But before we get there, during melting, the energy added to a substance equals the difference between the total potential energies of the particles in the solid and liquid phases. So this is known as the heat of fusion. So during melting, your energy that's added, that's going into decreasing those bonds, is known as the heat of fusion. So the latent heat during melting is the heat of fusion. During vaporization, the energy added equals the difference in potential energies of liquid particles and gas energies. So this latent heat is called the heat of vaporization. So this, back on this graph, this change in heat here, this is the latent heat of vaporization. This change in heat here is the latent heat of fusion. So we're going to practice this here on our graph. It's not a great picture, but I really liked this question. From the heating curve of a 15-gram sample, estimate the following properties of the substance. Now remember, 15 grams is 0.015 kilograms. You're going to find first, we're going to look at the specific heat capacity of our liquid. So we're looking for C. We're looking for C, and it's the specific heat capacity of this liquid. So we have a mass, it was told to us, 0.015 kilograms. We have this Q, how much heat was added. We have 15.8 subtract 8.37, that's our Q. And we can estimate our change in temperature. So we're gonna take our C is equal to Q divided by our mass times our change in temperature, and just estimate your temperature and you can figure that out. Number B, they're looking for the latent heat of fusion. So remember, that's solid to liquid. And the latent heat of fusion, what we're gonna do is we're gonna find our Q, and the latent heat of fusion, remember this is L, so L is equal to Q divided by M. So we have our 8.37 subtract 1.27 divided by the mass of our substance gives us the latent heat of fusion. So you should be able to answer the last two questions on this graph, and that's it.